Hi, I'm Leemon Baird, and I'm going to go through some slides that are based on the Swirlds Tech Report 2016 number 2, 2016-02. This is our second tech report of 2016, and these slides go through an example of the Hashgraph consensus algorithm. So step by step, you'll see how is it that a group of people come to consensus on the order of events in a hash graph. And actually, since we do virtual voting, it's really how does one person look at a hash graph and tell what the consensus order is. And so that's what this slideshow is. It shows you how a person looks at their hash graph in memory and can tell what order the events are in. The blue words are the words I'm defining. The hash graph is this picture on the left that we are slowly building up, lines and circles. It is a graph in the mathematical sense. Each circle contains a couple of hashes, and so it is a hash graph. The members are the computers. They are the full nodes in this network. Alice, Bob, Carol, and Dave are the 4 computers, and we've labeled them A, B, C, D. And each of them in this picture started off by creating an event. An event is a circle. It's a container for transactions. It's like a block in blockchain. Although typically we create so many of them that we can get away with smaller ones. So you might have fewer transactions in each event. And you can even have an event that's empty if you want to, with no transactions in it. You can see in this diagram, each of the people have now created one event, that's what they're starting with, and time is going to flow uphill. So the bottom of this picture is the beginning of time, when each of the members has created one event. Now, our goal here is to have some way for us to stop an attacker from shutting down the network or freezing the network and stopping us from reaching consensus. We want to be able to continue to have consensus even when there's a distributed denial of service attack against some of our members. So in a leader-based system, it's really bad when somebody has a bunch of cameras on the internet that have been hacked that are flooding the leader with packets. But here, we're going to try to make it so that you can't just shut down one computer and have the whole network shut down. It'll be resilient to that. We're also going to try to stop an attacker from giving us conflicting consensus. That would be far worse, where Alice thinks that we have reached consensus on an order, and Bob thinks that we've reached consensus, but they've reached different consensuses. If that happens, you lose. Byzantine fault tolerance means we have a math proof that that will never happen. So we do not want an attacker to be able to make us think that we've reached consensus when we haven't. That would be horrible, and have differing opinions on the order. Also, we're going to do something new. We're going to have fairness in our ordering. We want it to be hard for an attacker to unfairly influence what order we come up with. So if Alice creates an event with a transaction where she's bidding on a stock in a stock market, and then Bob sees what she bid and he comes up with his own bid, and he sends it out to everyone a little bit later than when Alice sent it out to everyone. When we finally reach consensus on which one was first, we need Alice to be before Bob. It should not be possible for Bob to do some evil attack that puts his first, even though in real life his was received by everybody later. In fact, we don't even want Bob to be able to recruit a few evil cohorts, evil conspirators to help him and to do this. We want to be safe as long as less than a third, say, of the population is being evil. We want to be safe from manipulation of the order. And that's something new. You don't have that in a blockchain, because in a blockchain, a miner gets to choose what's in his block. And you don't have that in a leader-based system like Raft or Paxos or some of the other leader-based systems, because the leader can reorder transactions coming in. We want to have a system where no one can easily influence what transaction order we end up agreeing on. So, one thing we're going to do is build this on a gossip protocol, because that makes it far more resilient to denial of service. A gossip protocol means there is no leader, there is no one in charge, there is no round robin where we take turns talking. It's just everybody talks to everybody randomly all the time. So you call another computer and you tell them everything you know and they tell you everything they know. Maybe Alice calls Bob and tells him everything she knows, and then he tells her everything he knows. And then Alice calls Dave and does the same thing. And then Alice calls Carol and does the same thing. And meanwhile, everyone else is doing it too. Bob calls someone at random, and then Bob calls someone else at random. Everyone is talking to everyone at random. There's no way to distributed denial of service attack one computer and hurt the network because everyone's just talking to everyone randomly. And there's no way to even slow down. When Alice inserts a new transaction into the network, there's no way to slow it down. You can shut down Alice's computer, of course, but if you don't shut down Alice's computer, her transaction is going to spread at the speed of gossip. It's going to be as fast as the grapevine in an office where you work. It's going to spread exponentially fast. And so by randomly talking to each other, information spreads out exponentially fast. And unless you can shut down, a full third of the network or even more, you're not going to be able to slow down the progress. Everybody's going to learn things incredibly fast. If you have 1 million nodes talking to each other, then in 20 syncs, your message gets out to everybody. And if you're syncing 20 times a second, then in 1 second, your message gets out to everybody. And there's just no way to shut down the network unless you attack lots of nodes. So, in this diagram, Bob calls Dave, and Dave creates a new event to commemorate the sync event of Bob having called him. So what you can see in this diagram is that Dave has created a new circle. Time flows uphill, so it's the second one up, and there is a line going down to Dave's first one, and also a line going down diagonally to Bob's first one. And this is commemorating the fact that Bob told Dave everything he knows. Of course, at this point, everything he knows is just one event. And that's what we're gossiping, is the events themselves. So Bob called Dave and told him one event, and Dave said, "Thank you. I will remember forever that you called me and gave me that one event, and I'm creating this new event to show it." Now, that event has the 2 lines going down, the diagonal one and the straight one. The diagonal one is the other parent, and the straight one is the self parent. Your self parent is the last time you created it, and your other parent is the other guy. And you can see this diagram shows an event as a giant circle with the 2 lines coming down and 2 hashes. So an event is just a little sequence of bytes in memory, not very many bytes, unless you have a giant transaction. But if you have reasonable sized transactions, it's a very small sequence of bytes. And we take a cryptographic hash of it, which is a way of compressing it down to very few bytes, maybe 32 bytes. And it is incredibly hard to find some other event that would hash down to the same cryptographic hash. That's what cryptographic hashes are for. It's hard to forge something else that would have the same hash. And so, this new event that Dave is creating contains within itself the hashes of Dave's previous event and of the last event Bob did before the sync, before Bob told Dave what he knows. Now, there's also a timestamp in there. Dave is allowed to make up a timestamp and put it in this. If he's honest, he'll try to do his best to put in the correct timestamp. But if he's dishonest, he might lie. He might put a timestamp 1 million years in the future, 1 million years in the past, or just subtly wrong. And maybe the clock on his computer is off, and so, his timestamp's wrong by a few minutes. But it doesn't matter. No one's going to trust this. It's more like one vote for what time this thing happened. What we're really going to do is we're going to take a whole bunch of timestamps and average them or take the median of them to try to figure out consensus timestamps on things. So this is just his claim as to when he created the event. It doesn't really mean anything until the community as a whole combines a whole bunch of them. But we have it. We have timestamps in every event. Once Dave has created this event, he digitally signs it. So for the rest of eternity, he has this proof that he created it. Other people pass it around, and you always know, when Alice gives Bob this event, you always know that it was created by Dave, and no one can forge it. And you know what its ancestors were, what its 2 parents were because of those hashes, and nobody can forge them. And so the whole structure is constantly tied together into a single, immutable, provable whole by these cryptographic hashes and these cryptographic signatures. So it's secure. And by the way, that's all we need for cryptographic stuff. We don't need anything exotic. We're not even using threshold signatures here. We aren't even using zero-knowledge proofs. All you need are ordinary signatures and ordinary hashes. And then, of course, we'll use SSL or whatever over the internet to keep it secure. And so you would use symmetric encryption for that. So it's all very generic. If you want to swap out the standard algorithms for quantum resistant algorithms, you can do that. It's all very straightforward. And so we're not reinventing the wheel. We're using traditional, well-tested, time-tested cryptographic things to keep everything safe. Now, that was what happened when Bob called Dave and told him everything he knows. Typically what you do then is Dave will turn around and tell Bob everything he knows. As long as they've already got this comm channel going, they might as well turn around and tell him the other direction. And so now you see this line from Dave to Bob, telling Bob everything he knows. Now when Bob told Dave everything he knows was just one event. All he did was handed Dave one event. Dave, however, is going to be giving Bob two events. It's his original event and the second event which commemorated Bob sending him stuff. So now Bob knows two events, and he has digitally signed his new event, and his new event has the hashes of his previous event and of Dave's latest event. And so everything ties together. And similarly, if we continue, now Bob calls Alice. He sends her all four of the events he knows about. That's his two events and Dave's two events that he received from Dave. And Alice creates a new event commemorating all of those. And so now we have 6 whole events tied up in one inside of Alice's new event. And this just continues. Typically, Alice will turn around and send it back to Bob, but she might not. Who knows? Maybe their sync gets interrupted in the middle, and so we just have the single one. But we just keep growing, and we grow upwards over time until you have this giant graph. Every event can have some transactions inside. Every event has the 2 hashes of its 2 parents. Every event can have some transactions. If the creator of the event felt like creating some transactions, it can be empty if they didn't. But this is the hash graph. It's a graph held together with hashes. This hash graph spreads at the speed of gossip, exponentially fast. As soon as Alice creates a new event, it just spreads like wildfire through the network, and pretty soon everybody knows about it. And so what you typically find is that this thing grows upwards, and everybody has exactly the same hash graph in memory, except at the very top, they haven't yet got the same stuff. But within a second or two, then everybody has, that layer, and now it's grown up even further. Now, when you have this hash graph in memory, you want to be able to look at it and put all the circles in an order, put all these events into an order, and you want to do it in such a way that everybody gets the same order. And you might say, well, we can just run an algorithm. In fact, we could run any deterministic algorithm and we'd all have the same order, which is true, except there's some corner cases that we have to deal with. And so everything I'm showing here is showing all the complexity that we do to take care of those corner cases. But the basic idea is, well, as long as we all run the same algorithm, we'll all come up with the same order, period. Or another way of looking at it is, traditionally in fault-tolerant computing, you could do this with rounds of voting. And we're going to do rounds of voting without the votes. Instead of us sending each other votes over the internet, we're all just going to stare at our local copy of this hash graph and pretend that there are votes going on. I will look at this and I'll say, well, if I were Alice, I know how I would vote if I were following the algorithm, because I know everything Alice knows. I know when she knew it. I'll just pretend of her votes. And so virtually, Alice will be voting in my head, and I can run some traditional algorithm with votes where I virtually let everybody vote in my head. And since everybody runs the virtual voting system in their head, everybody gets the same virtual votes, everybody gets the same consensus, and we're set. So, how do we do that? Well, the first step is we're going to divide up the events into the rounds. These are the rounds that they are created. In this diagram, they're created. There's a whole bunch of events down there in round 1. You only see 2 in this hash graph in round 4. As the hash graph grows upwards, I imagine we'd have a few more in round 4, and then eventually we'd have a round 5. I'll tell you later in the presentation the exact algorithm for how we pick up rounds, but the important thing is that when you're receiving new events for your hash graph, Every time you receive an event, you can immediately calculate its round created. You immediately know which round it goes in. Like that very top one on the graph, the moment you received it, you knew it was in round 4. There was no question, there was no voting going on, there was no waiting until I get some more to get some more information. The instant you received it, you looked at all its ancestors and you said, this is a round 4 created, has a round 4 round creation, and this is a round 4 event. All right. And if you're interested, it's when the supermajority of the witnesses in the previous round can be seen, strongly seen. But we'll get to that in a second. The important thing is that there is a way to divide these up into rounds. Now, why are we dividing them up into rounds? Turns out, by doing so, we can make the calculations much, much faster. And the reason is we can get away with only doing the expensive stuff on the witnesses. Look at the red ones. The red ones are the first events in each round created by each member. So look at Alice's column. The first event that Alice has in each round is colored red. The rest of them are just left gray. If we had 1,000 people, 1,000 full nodes, then you would find that only 5% of all the nodes are red. All the vertices are red. 95% of them would be gray. And it's only the red ones that have to have a fair amount of calculations being done on them. And so the fact that we divided things up into rounds lets us pick the first by each person in a round, which is called a witness, and that lets us narrow down our expensive calculations to just a 20th of the population if there's 1,000 of us. With 4 of us, you can see there's a little bit higher fraction, but still, most of the vertices in this graph are gray. It's a minority that are red. And so we've saved time. All right. And for convenience, we've also put numbers on these. So B2 is Bob's first event in round 2 with a round created of 2. That's what B2 is. And I wrote a B2 on the red one there. All right. And if you're a cheater, you could actually get 2 B2s. If Bob is a cheater, he could get 2 B2s. And you have to worry about that, and you worry about it, and it actually is why we're doing weird things with strongly seen that we'll get to in a minute. But all the math theorems say, doesn't matter, won't hurt anything. If Bob tries to cheat, he will do no damage to the network. Everything will work well. And so I'm not even going to show you cheating here. It's just part of the math. Because we can prove that just turns out this algorithm stops cheaters from doing any harm. Okay. So we have the round created for every event. We have the witnesses, which are the first. By the way, if you're not syncing very often, you might have a round where you don't have any witnesses. And that's fine. Alice doesn't have to have a witness in round 2. She could have skipped round 2. In fact, if you look in round 4, Alice doesn't even have a witness yet. And if we let this run for a while, maybe Alice wouldn't get one. Maybe Alice turned off her computer. And so for rounds 4, 5, and 6, she won't have any witnesses. No problem. Now, the important question for a witness is this witness famous? Famous means lots of people see it in the next round. So look at B2. B2 is the witness that we're going to talk about. The question, is B2 famous? Now keep in mind, we're eventually going to look at this question for every witness in the world. We don't bother on the gray ones, but for every red one, we're going to have to figure out, is it famous or not? But I'm going to spend the next few slides just talking about B2. Is Bob's witness in round 2 famous or not famous? And so we're going to hold an election to decide if he's famous. An election is a whole bunch of rounds of voting where we as a community will decide, is B2 famous or not famous? And ideally what we would say is, if B2 was seen by a bunch of people in round 3, then B2 is famous. And if B2 wasn't seen by a bunch of people in round 3, then B2 is not famous. So, let's look at round 3's witnesses. Those are the yellow ones. A3, B3, C3, D3. We want to ask, are those witnesses seeing B2 or do they not see B2? So let's look at it. Look at A3. A3 is one of those witnesses in that next round, in round 3. There is a path from A3 down to B2, a path of lines. And this path goes downward at every step. If you can show a path from A3 down to B2 that's always downward, that means that A3 can see B2. B2 is A3's grandparent. It's its parent's parent. If you start at A3 and you go to the self-parent and then you go to the other parent of that one, you get B2. And you can see your ancestors. And so A3 in this big election is going to vote yes. It's going to say, well, you know what? I can see B2, so I'll bet B2 is famous. At least I want to vote for B2 being famous. Now, if nobody else sees B2, then the election will say, no, there's too many no's, B2's not famous. But if lots of people vote yes, then B2 will be elected famous. So in this election, A3 is going to vote yes. Now, there will be other elections where A3 might vote other ways in other elections. But for the election on whether B2 is famous, A3 votes yes because it can see it. Now, there is a technical detail here. It isn't enough to be an ancestor. You also have to not see any forking. You have to not see any or not have any ancestors that are cheating. But don't worry about that for now, because we can just prove that as long as you put in that caveat, all the math theorems work. So for now, just think of it as A3 can see B2 because there's a path that goes downward the whole way to it. In other words, it's an ancestor. It's your parent's parent, or your parent's parent's parent, or your parent's 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 parent. Now, that's why A3 votes yes. You can also look at B3. Same deal. It votes yes because there's a line going straight down. And C3 votes yes because it has a line down to Dave, and then Dave has lines down to earlier Daves, and then the earliest Dave has a line down to B2, and so we have a path, and so C3 votes yes. And D3 votes yes because it has lines that go down and then sideways into B2. So it turns out that in this example, everybody voted yes. And it turns out that that is such an overwhelming majority that we're just going to say the election's over. B2 wins the vote. They are famous. Oh, but wait. An election's not over until you count the votes. Right now, all those events have voted, but no one has yet counted the votes. Now notice that I have not been talking about people. I have not been talking about members, about computers. All I've been talking about is events. It is B2, an event, that is famous or not famous. It's not Bob that's famous or not. And it's A3 that voted yes. It wasn't Alice that voted yes. It was A3 that voted yes. It was Alice's event that voted yes. And so just as it's an event that's famous or not, and just as it's an event that votes yes or no, so it needs to be an event that counts the votes. So the election's not over. We need an event to count our votes for us. So that would be an event in round 4, looking back at the events in round 3. In fact, it'll be a witness in round 4 to do the counting. So I told you the voting was based on just seeing. Counting votes is based on strongly seeing. You'll notice that red line from B4 to A3. It is following the black lines. Actually, that's an opaque line that I put there, so you can't really tell the black lines are there, but they're actually there underneath it. B4 does see A3 according to following these red lines. That's not enough. Because you see, that red line only goes through Bob and through Alice. To strongly see someone, you have to see them through a supermajority. That means more than 2/3 of the population. Now, you know, when the population is 4 people, the only way to have a supermajority is to have 3 or 4 people. 3 people is more than 2/3 of 4. So to have a supermajority, you need at least 3. A supermajority of 4. To have a supermajority of 100 people, you'd need 67 of them. So if you had 100 members, 100 full nodes in your network, you'd need 67 of them to be a supermajority. So for B4 to strongly see A3, it actually needs multiple paths that go through goes through at least 3 of the population, 3 different members. So the green line goes through Dave. So B4 does strongly see A3. If you look at the red line and the green line, it's going through 3 different people, and so 3 different members, and so B4 does strongly see A3, and so as we're tallying the votes, B4 says, yep, I see that first vote, and it is a yes. Now you'll notice that B4 actually doesn't see A3 through Carol. Poor Carol is left out, but it doesn't matter because Alice, Bob, and Dave together form a supermajority. So B4 did not have to see A3 with a path that goes through Carol, and it doesn't, and that's okay. Now, here we talk about counting the vote from B3. From B3, B4 does see it. How? Well, through the red line and through the green line. The red line goes through Alice and Bob. The green line goes through Dave and Bob. And together, they go through Alice, Bob, and Dave. That's 3 people. That's a supermajority of the 4. So B4 does strongly see B3. And so B4 has managed to collect a second vote. And if you'll recall, B3 was voting yes. So the second vote is a yes. Similarly, B4 can strongly see C3. And this time the lines go through Bob, Carol, and Dave. Carol finally got to participate, and Alice didn't. But that's fine. We don't need Alice, because Bob, Carol, and Dave makes up more than 2/3 of the population. It's a supermajority. By the way, you'll notice that I say that B4 sees C3 through Carol. It's C3 itself sees itself, and so it counts as going through Carol. Similarly, on that green path, it's seen it through Bob, even though it just started at Bob. So you always see the start and the end of your path, and you also see anybody that you pass through on that path. And here it passes through D4, and so it sees Dave. So B4 has now collected 3 votes from A3, B3, and C3. So far they were all yeses. And B4 collects a 4th vote from D3, which is a yes. And again, you see the 3 lines. And again, it only went through 3 people. So we're done here. B4 was actually able to collect a vote from everyone. You won't always be able to collect a vote from everyone. Sometimes you'll only collect a vote from yourself. Sometimes you'll only collect a vote from less than 2/3 of the population. But in this case, it collected a vote from everybody. Now, B4 collected all those votes. It was unanimous. That is a supermajority. So B3 is famous. Let me say this again. When B2 is famous. Let me say it again. In the previous slide, B4 collected all those votes, and all those yeses were a supermajority from the population. It had yeses from a supermajority, so the election was decided as a yes. So B2 is famous. The rule is, if you collect votes from a supermajority voting yes, and maybe you collect some no votes too, but you have a supermajority collecting yes, then the election is over. It is decided. The election ends, and the answer is now known. B2 is famous. Similarly, if there were a node, if there were a vertex, an event that was able to collect a supermajority of no votes, then we would say B2 is not famous, and the election's over. Then you could say, well, wait, what if one event collects a supermajority of yeses and one event collects a supermajority of no's? Oh, that's impossible. This is a math theorem. That never happens. No, the math theorem is that if any event in any round, actually it's only witnesses, but if any witness in any round ever sees a supermajority of yeses or ever sees a supermajority of nos and manages to decide, then everybody will eventually decide that way. That really is the consensus. Everyone will get that consensus. We're good to just go with that. And when you're doing this locally in your computer, you can just end the election and stop doing any more calculations on that election. You're done. So that is what deciding is. We have now decided that B2 is famous. But now wait a second. What if B4 hadn't been able to get a supermajority of yeses or a supermajority of nos? What if it saw half and half? Or what if it didn't even see any supermajorities? What if it could only collect one vote? Well, then we would just try a different event. We would look at D4, Dave's witness in round 4. And maybe he would have a supermajority of yeses or a supermajority of nos. And failing him, then we would wait for Alice to get around to creating an event in round 4, and we would let her witness vote, and maybe it would get a supermajority. Or maybe Carol would have an event in round 4 with a supermajority. And so we'll just keep waiting, and maybe somebody will eventually have an event in round 4 with a supermajority. And if any of them do, then we will decide that B2 is famous or not. We're done. It is possible that we wouldn't have anybody decide that way, but let's not deal with that right now. We'll just go to more rounds in that case. For right now, let's look at C2. Since we've decided B2, let's go on and look at C2. Now in this case, you can see that C3 sees C2. So C3 will be yes. Remember, in the first round of a vote, you just do seeing. It's in the next round where you're counting the vote that you do strongly seeing. That's where the red and green paths, and you have lots of paths. But for the first round, it's just single paths. You just say, who can see C2? And right now you can see that C3 sees it and votes yes. The other 3 witnesses all vote no, because there is no path from A3 to C2. Alice's witness in round 3 just cannot see C2, and so it votes no. And B3, Bob's event, Bob's witness in round 3, cannot see C2. You can see there's just no line, no path in the diagram purely going downwards from B3 to C2. And so he votes no. He being the event. The event votes no. And then Dave's event there votes no. So we have an election where there were 3 no's and a yes. Now let's see if anybody can count those votes. Oh, yeah. We've already said that B4 can see all 4 of those witnesses. So B4, by the same argument as before, we could redraw those red and green lines again. B4 collects all 4 of those votes. And the 4 votes are no, no, yes, no. So B4 has now collected no, no, yes, no. That is a supermajority of no's. 3 out of 4 were no's. 3 is more than 2/3 of the population. So B4 decides no. And when you decide, the election's over. No need for any more calculations. C2 is definitely not famous. If we were to continue, all the other events would eventually agree that D2 or C2 is not famous. And so we're going to color it blue. We're going to use green for the famous witnesses and blue for the non-famous witnesses. So we have decided the election for C2 is over. Notice that the same witnesses voted in both elections, and the same witnesses did counts in both elections. And you've now seen 2 full elections. Okay, great. Now, if it is possible that we didn't ever decide in round 4, then we could go on to round 5. And all of the round 5 witnesses would have counted votes from round 4. And how will people vote in round 4? Well, they'll vote according to the majority of what they saw in round 3. So imagine if B4 had not been able to decide. If B4 had, say, seen 2 yeses and 2 nos, well, then it couldn't decide. So it goes with the majority of what it saw. And when it's a tie, it votes yes. We'll just break ties as always being yeses. So if B4 had seen 2 yeses and 2 nos, it would then say, well, I can't decide because there's no supermajority. I'll go with the majority. Oh, it's a tie. Well, ties go to yes. So I will vote yes. So that's what one of these witnesses does. It either votes yes or it decides yes. Or it votes no or it decides no. And so if nobody in round 4 can decide, then they all simply vote, and it will be the next round, round 5, where we try to count votes and decide. And if nobody can decide in round 5, then everybody simply votes in round 5, and we'll go to round 6 and see if anybody can decide. And if nobody can decide there, we'll go to round 7 and see if anybody can decide. And we'll just keep going. In normal practice, you always decide almost immediately. But theoretically, you could, if the attacker is controlling the internet itself, which is one of the things our theorems assume, is that the attacker can actually control all the wires and routers in the internet, then maybe they could keep us going for a long time, and so we'll do coin rounds. So say every 10th round will be a coin round. And so to summarize the normal rounds, what we say is that if you can collect a supermajority saying yes, you decide yes. And in a normal round, if you can collect a supermajority saying no, then you decide no. And if you decide, then the election's over. But if you can't, then you just vote with a majority of what you collected. And if it's a tie, you vote yes. And if everybody in a round fails to get a supermajority, then everybody in that round votes, and then it's the next round that ends up having to decide. But if you make it if you make it to the 10th round, then we use a different rule for just the 10th round. It's a coin round. Anybody who collects a supermajority merely votes that way. You could collect unanimous yeses, and you'll merely vote yes, because it's a coin round. You don't decide. No one ever decides in a coin round. And if you don't collect a supermajority, you flip a coin. Wait, what does flip a coin mean? It means that the event that did the collecting, which is a witness, it's an event, which was digitally signed by whoever created it. It has a digital signature. You take the middle bit of that digital signature, and if it's a 1, you vote yes, and if it's a 0, you vote no. So in a coin round, anybody that gets a supermajority just votes. They don't decide. And anyone who has less than a supermajority for yes or no will vote randomly by taking the middle bit of their signature. And so every 10th round is a coin round. That's there to make the math work out, but in practice, it's incredibly hard for an attacker to even make us get to the first coin round. You're just normally going to decide in the first round or two. But, theoretically, you have to have these coin rounds. And this has been true for 30 years. All of this voting-based Byzantine fault-tolerant stuff involves coin rounds and shared coins and all sorts of things. But in practice, we never have to worry about that. We're always going to decide very fast. That is the entire consensus algorithm for whether someone is famous, whether a witness is famous. So to recap, as soon as you get an event, you put it into a round created. And then the first event in each round is a witness. So we all know what created rounds were. We all know what the witnesses are. And then each witness, we have to decide if it's famous or not famous. We hold an election. In the election, the witnesses in the next round vote based on whether they see it. If they see it, it's a yes. If they don't see it, it's a no. And then the next round after that, each of the witnesses collects the votes and decides yes if it's a supermajority yes, decides no if it's a supermajority no. Otherwise, it just votes with the majority of what it collected. And if it's a tie, it votes yes. And then if nobody in that round can decide, we go to the next round, and let somebody there decide. And if no one decides there, we go to the next round. And then every 10th round, we have a coin round where supermajorities vote with the supermajority and non-supermajorities vote randomly by taking the middle bit. Done. And the theorem is we will always decide eventually, with probability 1, we will always decide whether a given witness is famous or not. And it's kind of magic, and the magic is in the math. Everybody will decide the same way. So if I on my computer look at this hash graph and decide that B2 is famous, you on your computer will also look at the hash graph and decide that B2 is famous. And there's no way that an attacker can make me decide yes and you decide no. That'll never happen. We will always decide the same way. And there's no way an attacker can stop us from deciding. It is guaranteed that eventually we will both decide that B2 was famous. And so if we continue, eventually we will know for every witness whether it's famous or not. In fact, in this diagram on this particular hash graph, all those green ones we will decide are famous. And that blue one we will decide is not famous. And the red ones we don't know yet. We have to wait another fraction of a second until the hash graph grows upwards and gives us a few more events and a few more witnesses, and then we will know if some of those red ones are red or green. In fact, if you download the Swirlds SDK from swirlds.com, it has a bunch of demo apps you can run. And one of the demo apps is called Hashgraph Demo. And it runs this algorithm and shows you the hash graph growing right before your eyes. And what you discover is very much like this screen. Most of the witnesses are green. Occasionally there's a blue witness. And only the top 2 layers are red. It's incredibly rare for anything other than the top 2 layers to be red, which means that as soon as a witness is known, almost immediately, in a fraction of a second, we discover whether it is famous or not. We get the consensus. Now, the funny thing is that once we all agree on who the famous witnesses are in a round, then it is incredibly easy to turn that agreement into an agreement on the total order, and the agreement will be fair, and an agreement on a consensus timestamp for everything, and that will be fair, and it will all work, and it's obvious that it all works, and all the fancy subtle math is over with. It's all obvious from this point on. The hard part was to agree on who is famous, which witnesses are famous in each round. That was the hard part, and we're done. We're done with the hard part. So, now for the easy part, let's play with the gray ones. The gray vertices in this graph, the gray events, are still events. They still have transactions in them. We still need to know what is their consensus order. We still need to know what is their consensus timestamp, and we're going to use those green ones to set it up for us. And we're going to do it in pretty much the obvious way, like this. Look at the gray event that is now colored black. We want to know what round was this event received by the whole community. And the way we're going to do it is say, what's the first round where all the famous witnesses can see it? So you look in round 1 and you say, well, of course, those witnesses can't see it because it's later than them. So then you look at round 2 and you say, the red, green, and blue lines show that A2 can see the black event, B2 can see the black event, and D2 can see the black event. Now C2 can't see it. There's no line from C2 to the black event. But it doesn't matter because C2 is not famous. We're simply looking for the first round where all of the famous witnesses, all the green events, are able to see it. And so here, because all of the round 2 green events, famous witnesses, can see it, we say it's received in round 2. Now, if it hadn't been visible in round 2, we'd have to look up at round 3 and say, well, okay, if A3, B3, C3, D3, whichever of those are famous, can all the famous ones see it? But we don't have to do that, because in this particular case, in round 2, all the famous events can see it. So the first round, where all the famous events can see it, is its received round. we're going to say that that black event was received in round 2, meaning that the community as a whole received it in round 2. That's what we're saying. We also want to know the consensus timestamp on it, not just its received round. So what we do is we say, okay, the 3 famous events are A2, B2, and D2. They were created by Alice, Bob, and Dave. I want to know, what was the earliest time that Alice had an event that could see the black one? And what's the earliest time that Bob had an event that could see the black one? And what's the earliest time Dave had an event that can see the black one? And so in this particular case, for Dave, the earliest event is D2. For Bob, the earliest event is B2. But for Alice, the earliest event is the black one itself, because it can see itself. And so if we look at the earliest time, we're going to get 3 timestamps. It'll be the timestamp on D2, because that's the earliest time that Dave saw it. It'll be the earliest timestamp on B2, because that's the earliest time Bob saw it. And it will be the timestamp on the black one itself, because that turns out to be the earliest time that Alice saw it. So that gives us 3 different opinions on when the black one was received by the universe. And we just take the median of those 3 times, and that is the median timestamp. That's the consensus timestamp. So what we say is, when did the black one occur? When was it received by the community? It was received at whatever the median of those 3 times are. So we now know its round received, which is round 2, and its median timestamp, its consensus timestamp, which is the middle of those 3 times. We sort them in order and take the middle one. And that's all we need to know for black, for the black event. And now if we do that for all the events, we can put them in order. Now look at the gray event below B2. You'll notice that it's seen by B2, but it is not seen by A2, and it is not seen by D2. It was not seen by every single famous event in round 2, and so it doesn't get to count as being received in round 2. It'll end up being received in round 3 or round 4 or something. I don't know what. And so we'll have to wait a little while until the Hashgraph grows a little bit taller, and then we will know which events are famous in round 3, and then we'll see if all those famous events can see the gray one, which I think in this picture they will. And then we'll be able to say, yes, the gray one is received in round 3. But for the moment, all we can say is, well, it's not round 2. It must be received later. So we'll leave it colored gray and not black, because we don't yet know when it's received. So if we do this repeatedly, what do we discover? We discover that these 6 black ones are all received in round 2. And actually those 4 dark green ones at the bottom are also received in round 2. So we're coloring dark all of the events that have been received by round 2. And the 4 green ones are green because they are witnesses, but they're dark because we know when they've been received. They were received in round 2. There's 2 little gray ones right above the black ones, and that hasn't been received in round 2. They'll probably get received in round 3, but if not in round 3, then probably in round 4. We'll worry about them later. And so this is how we tell. When we want to put everything in order, we first sort all the events by the round received. So all the events that were received in round 2 are going to be adjacent to each other in the final consensus order. Then, to break ties in round received, we sort by the median timestamp. So for the 10 events in this diagram that were received in round 2, for those 6 black ones and those 4 dark green ones, they were all received in round 2. We sort them by their median timestamp. Now it's possible that that 2 of them have the same round received and the same median timestamp. And in that case, we compare the extended median timestamp. You get the median timestamp by having a list of times that are sorted and you take the middle one. The extended median is you look at the whole list and you zigzag back and forth. And then if that one doesn't even work, you actually sort them by the digital signature on each event, XOR'd with a random number, and that ensures that you can't rig your signature to come early. So basically, we sort everybody by the round received. When there's ties, we sort them by their consensus timestamp. When there's ties in that, we use something a little bit more complicated, the extended timestamp. And when there's ties in that, we're basically flipping a coin, but we're doing it in such a way that everybody gets the same answer, and there's no one has the ability to rig it. And so it really is random and beyond anyone's control. In other words, we end up with a very fair ordering of these timestamps. When your message goes out, it spreads out exponentially fast, it reaches everybody very fast, and it gets recorded in history according to the order in which it reached everyone. And nobody can cheat. That is what happens. And so we're done. We've put all the events in order, in a consensus order. Everybody agrees on the consensus order. Whatever transactions are inside of those events just ends up in the order that the events got in. And within a transaction, or within an event, if there's multiple transactions, it's just whatever order they were stored in it. So when Alice creates an event, she can put several transactions of her own in it, and she can put them in whatever order she wants. And then it all gets put into a fair order. And then they all get a consensus timestamp. And so every single transaction ends up with the consensus timestamp of its event, and we have this fair consensus timestamp on everything. And that's it. This diagram that we've been going through is actually not terribly unrealistic. In fact, it was based on the screenshot that you see in the middle there. That screenshot came from the Hashgraph demo, and it ran. This was showing a little region from round 100 up to round 105. And basically the top half of that screenshot is the diagram we've been working through. I changed it slightly to make it a better example, but it's basically the top half of that screenshot. And so what we've been working through has been a real run of the program, and we've been going through it. The reason I used that particular screenshot was that we finally had a blue event. This was a witness that wasn't famous, and I wanted to show you a witness that wasn't famous. That's actually fairly rare. Most of the witnesses end up being famous. And that's it. I hope that was helpful. Feel free to get in contact with me if you ever have questions about this, and you can also read the 2Tech reports. Well, thanks.